Welcome to Chapter 4, Atoms and Elements. We're going to start this chapter off by talking about some history, some very basic history of chemistry. So, to the naked eye, it seems that matter is continuous, or in other words, it can always be divided into smaller and smaller pieces. If you take a little tiny bit of something and you take a very tiny knife, it seems like you can just keep cutting matter into smaller and smaller bits. But in the 5th century, a philosopher named Democritus, I believe I'm pronouncing that correctly, is the first known person to theorize that you could not actually keep dividing matter into smaller and smaller pieces. You would eventually get to some tiny indestructible particle that he called atomos, which is where we get the word atom, because that means indivisible. And so this was the very first time that the idea of a basic building block of matter was put forward. Much later, in the 1800s, a guy named John Dalton put forward a formal atomic theory to try and explain in a sense, the basic rules, if you want to think of it that way, of atoms and how the universe works in relation to atoms. So he had 3 basic parts to this atomic theory. Number 1, each element is composed of tiny indestructible particles called atoms. And this is mostly true. We now know that this is mostly true. The reason why I say mostly true is because, as we will talk about in the nuclear chemistry chapter, atoms aren't technically indestructible. You can convert one atom into another kind of atom. It's just very difficult to do. And so, for the most part, that is true. The vast majority of atoms do not undergo nuclear changes to become something else. Number 2, all atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. Again, this is mostly true. The part about all atoms of an element having the same properties, that is true. All atoms of chlorine, for example, have the same properties, but it's not quite true that they have the same mass. As we'll talk about a little bit later, there are what we call different isotopes of elements that technically have different masses. And then the last part there, atoms combine in simple whole number ratios to form compounds. So you can take whole numbers of different atoms, combine them together to make some new thing called a compound. And this is 100% true. There are no exceptions to this rule. Unlike the first 2, where we had some rare exceptions, there is no exception to the fact that you can only combine atoms in whole number ratios. You will never find a water molecule or any molecule that is H1.5O. There's no such thing as a half of an atom or a quarter of an atom or anything like that. They always combine in whole number ratios. Oops, sorry, skipping over stuff there. So, building on this atomic theory, which for its time, for being in the early 1800s, that was a really good theory. That is almost completely true still today, when we know so much more about the fundamentals of the universe. So for its time, that was an amazing theory, but it was not 100% true, like we said. And what's more, it wasn't quite complete. And so even though it did explain a lot of things, and it was fairly accurate in how it explained those things, it was missing pieces. There was stuff missing. So later, in the 19th century, there were more questions raised about the structure of the atom itself, and people started to theorize that maybe the atom is not actually the smallest thing. Maybe the atom is actually made of other stuff. and there was an experiment done, I want to say by Thomson, I think was his name, J.J. Thomson, but I could be misremembering that. But anyway, there was an experiment done where it was proved that there were actually smaller particles than atoms, and these were called cathode rays, is what they were called at that time. We now know them as electrons. Actually, it says right there. I should read my slides. So Thomson discovered the electrons. And so when they tried to fit these electrons into the idea of the atom, there were a few different competing theories. The theory that got the most traction early on is what's called the plum pudding model. And this plum pudding model essentially stated that the vast majority of the atom is this positively charged goop, and the electrons were known to be negatively charged. That's why the goop needed to be positively charged. And so these negatively charged electron particles were dispersed in this positive goop, this pudding-like material. And so this was this plum pudding model, which was accepted and taught for a while until another scientist named Rutherford designed an experiment that was built to try and determine if the plum pudding model was correct. This is what we call the gold foil experiment. And in a nutshell, what this experiment was trying to show was that if the plum pudding model was correct, if you take a radioactive source, that's what this is here, and you let alpha particles come shooting out of that radioactive source. Alpha particles were known to be things that were essentially tiny little atoms. I don't want to get into the weeds here and explaining exactly what alpha particles are, but they were essentially tiny little atoms. They're bigger than electrons, but smaller than the gold atoms that are in this piece of foil here. So if the plum pudding model was correct, because the alpha particles are a lot bigger than electrons, and because the alpha particles are super high energy, they're very, very high energy particles coming out of this radioactive source, the alpha particles should just blast right through that gold foil. The gold foil is very, very thin, so there's only it's only really a few atoms thick. Well, it may be more than a few, but it's very, very thin gold. Think gold leaf, if you've ever worked with that before. It's very, very thin gold, but it is still solid. It is a solid piece of gold. It's just very thin. And so the alpha particles should blast right through if the plum pudding model is correct, because they would have more than enough energy to blast through the positive goop, and the electrons are too small to deflect them. They're too small to bump into them and get deflected off to the side. And what they saw was that, in fact, most of the alpha particles did go straight through. Most of them went straight through the gold foil and impacted right on the other side of the detector here. There's a few that deflected just a tiny little bit, and that could possibly be explained by the electrons. Maybe, the electrons can't deflect the alpha particles very much, but maybe they could deflect them a little bit. But then there were other alpha particles that when they went into the gold foil, not only did they not go straight through, but they deflected a lot. Maybe even at right angles or even back towards the source. And there is nothing in the plum pudding model that could explain how this relatively large alpha particle could be smashing into something and bouncing off of it back into the opposite direction. There's just nothing in this model that could account for that. And so Rutherford developed a new theory, what he called his nuclear theory of the atoms. And so this is what they expected to see here, the alpha particles just blasting through the plum pudding. But instead, because most of them went through, but a few of them deflected off in different directions, Rutherford proposed that instead we had a very small area of the atom that was really dense. So nearly all of the mass is here in this little area of the atom, and so when the alpha particles would hit that, it would actually deflect the alpha particles off in different directions. But then most of the alpha particles would fly through this relatively empty region where the electrons were floating around. And so this described what the results they saw very, very well. And so these were the three main points here, and a couple of these I've already kind of mentioned. So the three main points of Dalton's nuclear theory is that most of the atom's mass and all of its positive charge are contained in a small core called the nucleus. That is 100% true. Nearly all the mass is in the nucleus. The electrons are very, very tiny compared to what's in the nucleus. Number two, most of the volume of the atom is empty space, through which tiny negatively charged electrons are dispersed. Again, 100% true. Number three, there are as many negatively charged electrons outside the nucleus as there are positively charged particles, or protons, as he called them, inside the nucleus, so that the atom is electrically neutral. And again, that is 100% true. It's possible for you to have atoms where this is not true, but those would no longer be considered atoms, they would be considered ions. And it's a bit of a technicality, but we'll talk more about ions in just a minute. Well, in another video, I should say. So these 3 points here, all 100% true. 100% correct. But again, kind of similar to Dalton's atomic theory, even though it is correct, it's still not quite complete. There's nothing here that's wrong, but you don't have the whole picture. And so later, as they began to study this more, they realized that there was some mass essentially missing in the atom. The protons that they knew were in the nucleus could not explain all of the mass that they saw in the nucleus. And so it was realized later that there were other particles in the nucleus, which we now call neutrons, that are neutrally charged. So they're neither positive nor negatively charged, but they do have practically the same mass as a proton. They're nearly identical to the mass of a proton. And so with those 3 things, our atom is complete. Our structure of the atom is complete. And I think we'll go ahead and call it here for this video, so just make this the history video. And the next one we will pick up and talk about these 3 different components of the atom and how they relate to each other inside of the atom. So I'll see you in the next video.